Hello and welcome to our Advanced Computer Engineering Group project. I'm here to present to you the Multi-Nodal Environmental Sensor System, MES. Now the aim of our project is to build a sensor that is able to sensor and monitor the different environmental variables such as CO2, carbon monoxide, humidity and temperature. Now the reason for us to do this is because we want to build a device that's able to aid environmental scientists to be able to collect large and vast amounts of data of different variables in the environment, for them to be able to analyse any of the data that is stored in the database due to the sheer amount of data collected.
For this project, we're using the Odroid C2, which is a single board computer based on an ARM processor. It's low cost and low power, so it would be suitable for having multiple nodes spread out around the place. We are looking to use the GPIO pins on there in order to bring in data from external sensors, which can then be processed using a number of different software languages. So we have the option of C, Python, among others.
On the Odroid, we wanted to have a multitude of different sensors, such as MQ sensors, that were suitable for a wide range of gases, such as carbon monoxide, carbon dioxide, and nitric oxide, which are leading contributors in global warming. There were other sensors that we wanted to have, such as humidity and temperature. There were others, such as G-force. We wanted to have a GPS installed on each of the nodes so that we can differentiate between the sensor values that we read in different locations. There were other sensors such as air pressure, which we wanted to have installed as well. And we wanted to have all these readings transmitted and displayed at our base station. We can see them on the GUI.
This is the circuit diagram for the multi-nodal environmental sensor system. We take 5 volts and 3 volts straight from the Odroid along with ground. From there we wire up our digital sensors, which all run on 3 volts, and they also have a logic level of 3 volts, and those are wired to various digital GPIO pins on the Odroid. The MQ gas sensors are wired up through a multiplexer, with GPIO pins being used to drive the selector pins. And according to the selector pin that we choose, we select a different sensor from the list.
Did you want me to do it now?
Once we've done that, we get the readings from the sensors sent back through to the analog pin of the Odroid, and that goes through a level shifter, a voltage divider circuit, to drop it down to the 1.8 volts maximum that is allowed on the Odroid.
Go.
So one of our sensors we're using would be the GPS, and the GPS we're using is near 6 receiver, and we basically choose that because it gives the accurate position, velocity and time. I'm looking.
No, it doesn't.
Yeah?
Go on.
So it has got high sensitivity and tracking capabilities. It operates on the range of a voltage range of 3.3 to 6 volts, which is really low, and it uses transmission and receiving. It uses UART protocol to communicate, which has got transmission and receiving ports, and it is using U-block 6 protocols to communicate, which displays the longitude and latitude of the position of where the GPS is. It also uses NMEA communication protocol, which uses the GGA representation of the GPS, and that is on the GPS by default. It updates at the rate of 1 Hz by default, and the serial communication baud rate for the GPS is 9600 by default as well. And we're using PY and MEA library that helps read and pass NMEA data across. And as you can see here, for the GPS, we've got a transmission pin which is connected to the receiving pin on the Odroid C2. and the receiving pin on the GPS is obviously connected to the transmission pin on the C2.
The MQ sensors, which are used for the detection of various gases, are all based upon using WireInPy to communicate with the GPIO pins. So we are importing WireInPy Python library as WPI. The actual code for this is all set up in a class where we've got multiple sensors that basically act the same way. We can call the class within our main code as the various sensors. So for example, MQ2 would be its own object based upon the MQ read class, and then we could use that to grab various values from the MQ2 sensor. So when the class is first established and initialized, we go through the initialization function. In here we've got the option to calibrate it. In order to save time, we've decided to calibrate it first on its own, and then add the values of the calibration into the class itself. So here you see the various values of the RO, which is the resistance in clean air of a certain type of sensor. So for the MQ2, for example, we've got 3.468 kilo ohm as the RO value. The read analog function takes an input of the sensor selected and then uses a truth table to select the various sensor that we need to read from. We do this because the Odroid C2 only has 2 analog inputs and we are reading from 3 different analog sensors. So within here we set the pins to high or low according to what we need, and then we read in the ADC value. We actually take a sample of 10 and then we use that to calculate an average, which is then used for further calculations. Once we've done this, we can then use the MQ resistance calculation to basically work out how the resistance is changing according to the ADC reading. And then this is later used to determine the amount of gas that we're detecting based on parts per million. The way that we do that is via using the graphs from the data sheets, and we can actually figure out roughly what the reading would be in real world values based upon the curve that's created by the graph.
So one of the particular devices that we had to use was an accelerometer. Now the accelerometer is a device that can measure the acceleration or the vibration on a particular component and measured in G-force. And the one that in particular that we picked for this project was an LIS 3DH, which communicates via the digital pins rather than analog. In particular, this one communicates via I2C, which is a combination of SPI and UART protocols. So in particular, how it works is SPI communicates, it has a master and can select several slaves. So in this instance, it only uses 2 digital pins. The first transmitting data across the data line for RX and TX transmission, and then the second pin would be for a clock at the baud rate it would transmit at. Now, in this scenario, our Odroid C2 would be the master in particular, and the accelerometer would be the slave. And how it works is, what we do is we first have to communicate with the Odroid C2 bus, where the accelerometer would essentially connect via the digital pin, and on the bus we'd be able to see an address associated with that. We can use that address to essentially implement in our code, which we would use to start transmitting and receiving the values from the accelerometer. Once we've been able to connect to our particular sensor, the accelerometer, what we then have to do is we have to essentially interact with the different registers associated with that, which allows us to perform particular functions that we wanted to do. For instance, once we've selected the address, we can then pick a register that will do a particular function, for instance, enable the XYZ values, or for instance, deciding what type of G-force range we want to instantiate. And within those particular registers, there are further settings that you can do. So there'll be an 8-bit address, which you can use the hexadecimal value to essentially instantiate more settings within that. For instance, you want it to be a high or low frequency. Would you like it to be a particular power setting, and so on. So what we discovered when we first got the values from the accelerometer was that the sequence of bits was actually out of order, and then after some research we discovered that it was essentially running as a big endian, little endian, and big endian. So what that means essentially is the sequence of bits have been shifted, meaning the most significant bit is in the little or the least significant portion, and vice versa. So the way that we solved this problem was by essentially each essentially least significant and most significant bit were 16-bit values. So to get them in the right format, what we had to do was to shift by 8 bits for the big endian. Now with that, what you could do now is, once it's in that format, what you can then do is add the big end and little end in the right sequence. And that will give you your, in this case, our x-axis value in the right sequence of 4 bytes or 32 bits. So once we've received the data value from the sensor onto the Odroid, essentially what we discovered is it comes in this particular format where the least significant bit is situated on the right side of the full value and the most significant on the right. So to make it a bit easier to transmit across to our base station and to read the values in the correct format, what we needed to do was essentially shift the most significant bit to the right by 8. So in this format, what we can do is basically do simple arithmetic, where now we've got the most significant bit situated on the left side of the data value, and once we add that together, we can get our data value in the correct format.
Right, this is the script, the Python script for the DHT11, which is our humidity and temperature sensor. Here we have the initialization of the pins. This is where we set up the wiring pi, which is what we're using. And then here is the bin to dec, which basically turns the binary values into decimals, so we can read it. And then here is the pin outputs. So first we set it as high, we set the pins to high, and then we set the pins to low for 18 milliseconds as a request signal. And then from there we set the input to 0 and then activate the pull up resistor, which brings it back up. And then in a range of 2000 samples, it reads from the data pins and records it in an array. For the binary values received, if there is 15 instances of high, then the binary recorded is 1, and if there is less, then it will be recorded as 0. Here is where the humidity and temperature bytes are calculated. If the checksum passes, it returns true, and if it returns true, then the humidity and temperature values are then available through the main function.
Perfect, cool, thank you.
You got a lot of editing to do there.
Yeah. Cool, let's your chair back.
So there are a couple of different dongles that we looked at that we could give to the Odroid. Quite a few of them were between the 800 and 900 megahertz range, which would give us a lot greater distance than a 2.4 gigahertz range. But with the amount of data we're sending, we don't really need that high frequency. So we looked even further and we found this, which is a 435 megahertz dongle, which creates a serial port that can attach to the Odroid, and we can use it for that. The idea of in the actual structure of the network, what will actually happen is we'll have a base station that's located somewhere, and the idea is to create this wireless network as a mesh network. In that, if these are the ranges of each of these, then we can see that this sensor is out of range of the base station. So what will happen is that the communication for this sensor to get to the base station will route through this sensor and head to the base station. And in order to get the data to be transferred from the individual sensor units to a base station, which then can be displayed to a user or a system or anything like that, we're going to need to develop a way of transferring the data between the sensors and onto the base station. So different options available there. We could eliminate things like wired communication, because the idea of these sensors is to have them spread out, so plus 100 meters apart. And in, say, a cable, Ethernet or something like that, the signal would degrade over time and you'd require repeaters to be set between them. And there's the additional cost of actually laying the cable down and making sure that it's kept up to a good standard and it isn't damaged or anything by the weather or just people in the street. So with that in mind, we have to sort of move into wireless communication. So we need to send wireless signals between them. Out there right now, we've got things like Wi-Fi, which runs at 2.4 gigahertz. And we've got things like LoRa, which work on lots of different frequencies, similar to what's coming out soon with 5G. So it's just getting it there no matter what. The problem with the LoRa is that it's more of a concept right now. There isn't a lot of implementation for it. So we have to sort of look into other areas. The problem with some of the frequencies like Wi-Fi, which is very established and we could probably easily use, is that it's still quite low range because it uses a free license to access the radio frequency. It's limited to about 20 dB in transmission power, so that limits its range to approximately 100 meters or so in a free airspace, but in, say, more of an urban environment, probably only 30 meters or so. So to get around that, the options would be, we actually pay for a license for the radio frequency and we can actually transmit a lot more power and get a lot more range out of whatever frequency we choose. Unfortunately, that is quite expensive and we want to keep the cost low on the system. So the other option would be to maybe pick a free license that's on a lower band frequency that will allow us to get a lot further, because as with any RF transmission, the higher frequencies have a shorter wavelength and will lose their power quicker. Well, once we got the transceiver dongles that can transmit over 435 megahertz, we tried to look for any packages or anything we could use to devise a comm link between the different devices. So the first thing we did, we looked obviously online. We found that there is a point-to-point protocol which allows for two serial devices to talk to each other, provide a network interface. At first this seemed to work fine. Unfortunately, the problem with it was that the transceiver that we were supplied could only handle up to 180 bytes at a time, which meant that any of the main established protocols that we use across IP would be vastly too big, that nothing could really send. We couldn't send an SSH connection over, we couldn't send even a web signal. There wasn't really much we could do. So the only real way we could get around this issue but still use the equipment we acquired was to create our own protocol. So this is the design for the protocol that we ended up using. As you can see, we've got two main sort of packets. We've got a handshake packet and a transport packet. And the idea being that when any kind of communication was to happen between any of the nodes, the transmitter will first do an open handshake to the receiver and ask, are you there? The receiver can then confirm that they are there. The transmitter then is clear to send the actual data that it wants to send in this transport packet, and then the receiver will complete the handshake and close the connection. So here we can just sort of see the actual frame of each of the packets. So we've got protocol ID in the handshake that says what is a handshake. We've got packet ID just to try and make sure that all packets are unique and hopefully prevent anyone from doing repeating attacks. We also need to say who we're trying to talk to, who it is we are, and we just want to check CRC to make sure it was transmitted correctly. As you can see, that this is only 15 bytes long, so this should be well within the 180 byte limit. And then here we've got the transport packet, so this is made up similarly of the protocol ID, the packet ID, destination and source. Additionally here, because we wanted to create a sort of generic transport packet that can send whatever we wanted, so we don't have to stick to just the readings for the sensor, we could possibly set commands or who knows what. So this one is just a generic, there's data here for raw data or any kind of packet that goes above that relies on this protocol. So here we've just got 4 to 150 bytes, which is defined by this length. And then we have a check CRC, which would run across the whole of this packet up to this point, be inputted here. And then the whole point is that this area here is then encrypted so that no one can read or intentionally alter the data without it being flagged as incorrect or errored out when it gets to the other end. And then obviously over on top of that, we still have a check CRC to make sure just in general that the transmission was correct and no errors occurred.
Well, I was the GUI developer for the team. I was in charge of creating the GUI interface that displays the sensor readings collected from the multinodal environmental sensor system. Yeah, so each of the sensor readings displayed on the GUI consists of technologies like the CSS, which is used to control the presentation and the layout of the page, and the JavaScript, which is used to control the behavior of different elements. So my block diagram here explains the process taken to create the GUI. The HTML was written in a software called the Notepad++. The Notepad++ consists of the HTML, CSS, and the JavaScript. And each of the JavaScript contains the sensors, which are the temperature, humidity, GPS, the gas sensors, and the accelerometer, which is then transferred to the web browser and displayed on the Odroid C2.
As we can see on the left here, we've got a readout from the comms program that's running on this laptop, which has been the benefit of actually using C#, is that we can run it on any operating system that has the relevant framework. So on as I said, on the left here we've got the reading that would run the sensor code. On the right we've got a live feed from the base station just over here, which is actually receiving data wirelessly through the dongles. And we can see it's actually reading in the data, it's then making a connection to the MySQL database and uploading the data to that database. and then here we can actually see the web page that displays the data, and you can see it's displaying data. And if we, in this case, we're using test data, we're not feeding live from the real sensor yet, but we can show if we change something. We can then go to here, we can see that the temperature has changed.
Okay.
So as you can see here, this is our sensor system here. We have a collection of 6 sensors on the board itself. Towards on this side of you can see the accelerometer here. Here you can see the humidity and temperature sensor. This larger one over here is the GPS module, Neo 6, and collectively these 3 are the smoke sensors, the MQ ones.
So this is one of our nodes. We've got gas sensor, GPS, temperature, humidity sensor, and accelerometer, which is connected to the Odroid. The Odroid will read the readings captured by the sensors, which is then sent wirelessly through this to the base station, which is this. And as the values change, it can be seen on this web server. So basically, if we do a demonstration of the accelerometer, so while moving it, you can see the readings here will be changed. So if you move it, yes, so as he's moving it, the readings of X, Y, and Z changes. And as you can see here, we've got the map, which displays the location of the GPS, the readings of the gases, temperature, and humidity.
The Odroid C2 provided an ideal solution for a weather sensing and reporting system. The GPIO pins provided access to a number of sensors, but also brought challenges to get working. The Python WireImpy library needed was an older version only available direct from hard kernel. The functions created by the team as a whole were pulled together in the main Python function. Transmission across the 433 MHz frequency allowed data to be shared between nodes. The multi-node structure creates a system that could be implemented into a full product for use by environmental scientists.